The cosmos just delivered a shocking, almost unbelievable piece of news, the kind of scientific announcement that instantly rewrites major sections of the astronomy textbook. The James Webb Space Telescope, or JWST, has found a black hole with a mass millions of times that of our Sun, not nestled quietly and predictably inside a galaxy, but floating alone in the vast, turbulent space between two colliding galaxies. This finding isn't just a surprise, it's a cosmic violation of the rules, challenging everything we thought we knew about how the universe builds its most extreme objects, demanding that scientists re-examine the core processes of gravitational collapse. Get ready, because we're about to explore the incredible story of the Infinity Galaxy, James Webb's shocking evidence of a newborn black hole where none should exist, detailing the massive cosmic forces required to make such an impossible object a reality. Let's begin our journey by setting the scene for this colossal event, traveling 8 billion light-years away from Earth, a distance so immense it places the event long before our Sun and solar system were even born. To put this distance in perspective, light traveling at 186,000 miles per second, the fastest thing in the universe, takes 8 billion years to reach us from this location. That means we're not just looking across space, we're looking backward through time itself, witnessing events that occurred when the universe was significantly younger, wilder, and more violent than it is today. The photons of light that are hitting our telescopes right now began their journey across the cosmos long before Earth existed, before our Sun ignited, before our entire solar system coalesced from a cloud of dust and gas. What we call the Infinity Galaxy is not one galaxy, but actually a system of two massive, gas-rich disk galaxies locked in a deadly head-on crash. Imagine two giant frisbees, each made of billions of stars, vast clouds of gas and dust, slamming right into each other at speeds of millions of miles per hour. This is not a gentle sideswipe, it's a brutal, catastrophic event, a true cosmic smash-up of epic proportions that will take billions of years to complete. The sheer violence of this collision is almost impossible to comprehend on a human scale. If our entire planet were scaled down to the size of a grain of sand, these galaxies would still be objects of incomprehensible magnitude, containing hundreds of billions of stars, each potentially hosting their own planetary systems, all careening toward mutual destruction. The system gets its poetic nickname, the Infinity Galaxy, because the violent gravitational and gas interactions have stretched the stellar material into a distinctive, mesmerizing figure-8 or double-ring shape. It looks exactly like the mathematical symbol for infinity, a perfect, glowing knot of chaos in the deep black of space, a visual representation of endless cosmic power. This distinctive shape isn't just aesthetically striking, it's a telltale signature of the immense tidal forces at work. Forces so powerful they can reshape entire galaxies like clay in the hands of a cosmic sculptor. The rings themselves are composed of billions of stars that have been pulled from their original orbits and flung into these enormous loops, creating spectacular light shows visible from across the universe. The distance of 8 billion light-years is a crucial detail we must absorb. It means the light we are seeing now left the galaxies 8 billion years ago, since the universe is currently around 13. 8 billion years old, this collision happened roughly 8 billion years after the Big Bang, essentially halfway through cosmic history. This timing is important because it means the galaxies involved were already mature. They had gone through several cycles of star birth and death, enriching their gas clouds with heavy elements. Unlike the pristine hydrogen and helium clouds of the early universe, these galaxies had been cooking heavy elements in the nuclear furnaces of stars for billions of years. Carbon, oxygen, nitrogen, iron, and dozens of other elements had been synthesized, released into space through supernovae, and recycled into new generations of stars and gas clouds. This makes the discovery even more perplexing, as we will soon see. The galaxies involved were typical disk galaxies, similar in shape and structure to our own Milky Way, meaning they were rich in the cool gas and dust needed to make new stars. Each galaxy likely measured over 100,000 light-years across, comparable to our home galaxy, and contained hundreds of billions of stars arranged in beautiful spiral arms wound around a central bulge. When they first began this encounter, they were two separate, peaceful islands of stars, each revolving slowly and calmly, containing huge amounts of gas, specifically molecular hydrogen, the primary fuel for star formation. The richness of this material meant the collision had an abundance of raw material, the necessary fuel for an explosive cosmic event, specifically the immense amounts of dense gas required for black hole formation. Astronomers estimate that each galaxy contained tens of billions of solar masses worth of gas and dust, material that would normally have been slowly converted into new stars over the course of billions of years. But the collision changed everything, transforming this orderly star formation process into something far more chaotic and extreme. The presence of so much available material set the stage for the extraordinary events that would follow. Events that would challenge our fundamental understanding of how the most massive objects in the universe come into being. When galaxies collide, the physics of the accident is counterintuitive, almost paradoxical when you first encounter it. The billions of stars in each galaxy are so incredibly far apart from each other that they almost never directly hit. The distance between stars is so vast that the chance of any two stars actually touching is infinitesimally small, vanishingly unlikely even in a head-on collision. Think of it like flying two flocks of birds through each other, but the birds are spread out over distances that dwarf the size of Earth. In our own solar system, the nearest star to our Sun, Proxima Centauri, is over 4 light-years away, a gulf so enormous that even traveling at the speed of light would take over 4 years to cross it. To truly appreciate just how empty space is between stars, consider this. If our Sun were the size of a basketball, the nearest star would be about 4,000 miles away. That's the distance from New York to London. Now imagine two groups of basketballs, each group containing 200 billion basketballs, all separated by thousands of miles, passing through each other. The chances of any two basketballs colliding is vanishingly small. This is the reality of galactic collisions at the stellar level. But here's where it gets even more interesting. Even though individual stellar collisions are rare, the gravitational influence of all those stars collectively creates profound effects. Each star feels the combined pull of billions of other stars, creating what physicists call a gravitational potential. As the two galaxies interpenetrate, their gravitational potentials interact in complex ways, creating tidal forces that reshape both galaxies dramatically. Stars that were once in orderly orbits around their galactic centers find themselves pulled in new directions, their trajectories completely altered by the collision even though they never came close to hitting another star. The timescale of a galactic collision is another aspect that challenges our intuition. When we say collision, we might imagine a sudden, violent crash happening in moments. But galactic collisions unfold over hundreds of millions of years. The two galaxies in the Infinity System are currently passing through each other, a process that probably began tens of millions of years ago and will continue for tens of millions more. They'll pass through, their mutual gravity slowing both of them down, eventually pulling them back together for another pass, then another, each time getting closer and more entangled, until finally, billions of years from now, they merge completely into a single galaxy. The stars themselves rarely feel anything more than the gravitational tugs from the entire group. An individual star in a colliding galaxy experiences only the collective gravitational pull of all the other stars and matter, not specific close encounters. This means that if you were somehow standing on a planet orbiting a star in one of these galaxies during the collision, you might not even immediately notice anything was happening. Your star would continue on its path, tugged gently by the gravitational forces of the collision but not threatened by direct impact. The night sky would slowly change over millions of years as the arrangement of stars shifted, but there would be no dramatic, sudden catastrophe from stellar collisions. However, the gas and dust, which are sticky and spread out into continuous clouds, interact violently. When the two gas clouds meet, they can't just pass through each other. They crash like two giant waves of thick air slamming together at supersonic speeds. Unlike the stars, which can thread past each other like bullets passing through a wide-spaced net, the gas clouds are continuous media that must interact directly. This immense pressure and friction are the key to this whole story, generating unimaginable heat and turbulence as the kinetic energy of the crash is converted into thermal energy. The The force of this crash is enough to completely change the chemical and physical state of the gas. The energy released from this friction alone is enormous, far exceeding the energy output of all the stars in the galaxies combined. To put this in perspective, a typical galaxy might emit the equivalent of billions of suns worth of light from its stars. But during the most violent phase of a collision, the energy released by the crashing gas clouds can temporarily outshine all of those billions of stars combined, creating one of the brightest events in the universe short of a supernova or black hole merger. This energy manifests in multiple forms: intense heat that can reach millions of degrees, powerful shockwaves that propagate through the gas at thousands of kilometers per second, and brilliant emissions across the entire electromagnetic spectrum from radio waves to X-rays. As the galaxies pass through one another, the powerful gravitational forces, known as tidal forces, pull and stretch the material, distorting the smooth circular shapes of the galactic disks and pulling the stars and gas out into those enormous glowing stellar rings. Tidal forces are differential gravitational forces, meaning different parts of the galaxy experience different gravitational pulls. The side of the galaxy closer to its colliding partner experiences a stronger pull than the far side, causing the galaxy to stretch and deform like taffy being pulled. These tidal tails and bridges, as astronomers call them, can extend for hundreds of thousands of light years, creating some of the most spectacular structures visible in the universe. These rings are essentially new areas of massive star formation, where the sudden compression of gas acts like a cosmic trigger, instantly igniting thousands of new suns in spectacular bursts. When gas is compressed in these collision zones, its density increases dramatically, and when gas becomes dense enough, it collapses under its own gravity to form new stars. The compression acts like squeezing a sponge, forcing the gas into ever smaller volumes until critical densities are reached and star formation ignites. These bursts of star formation, called starbursts, are a common, expected sign of a galaxy collision. In some cases, a collision can trigger so much star formation that a galaxy creates more new stars in a few million years than it would normally create in a billion years of peaceful existence. But the real action, the most violent and crucial interaction, is in the space between the two galactic centers. Here, the gas gets compressed and heated dramatically, creating immense shockwaves and turbulence. Think of a gigantic, never-ending sonic boom, but on a galactic scale, spanning tens of thousands of light years. The gas is heated to temperatures so high that the atoms lose their electrons, a process called ionization, turning the neutral hydrogen into ionized hydrogen. At these extreme temperatures, typically millions of degrees, the thermal energy is sufficient to completely strip electrons from atoms, leaving bare nuclei surrounded by a sea of free electrons, creating what physicists call a plasma. The sheer force of the shockwaves is what creates this incredible environment of superheated ionized gas. These shockwaves travel at supersonic speeds, sometimes exceeding thousands of kilometers per second, compressing and heating everything in their path. When a shockwave passes through a region of gas, it acts like an enormous cosmic piston, suddenly increasing the pressure and temperature by factors of hundreds or thousands. The gas behind the shock is fundamentally transformed, turned from cold, neutral molecular clouds into hot, ionized plasma in the blink of an eye, cosmically speaking. This transformation is crucial for understanding the extreme environment that will give birth to our mysterious black hole. This central region, the intergalactic void, becomes a cosmic junkyard of compressed, angry matter. It's a place of extremes, incredibly high pressure, extreme density, and a whole lot of energy being released in the form of X-rays and radio waves. The X-rays come from gas heated to tens of millions of degrees, so hot that it radiates primarily in high-energy photons. The radio waves come from electrons spiraling around magnetic field lines at nearly the speed of light, creating a process called synchrotron radiation. Together, these emissions paint a picture of one of the most violent environments in the entire universe, a place where matter is being pushed to its absolute limits. This turbulence, this intense crushing of material, is what astronomers believe set the stage for the bizarre discovery. The gas that once floated harmlessly within the main body of the galaxies is now being stripped away, violently squashed together, and turned into a superheated, violent mash of hydrogen and helium in the intergalactic medium. the space between the galaxies. The gas is no longer spread out. It is focused and concentrated by the collision's crushing force into a dense central knot. This is a process called ram pressure stripping, where the pressure of the collision literally strips the gas away from the galaxy's gravitational grip and deposits it in the space between. This extreme environment is the critical character in our story, a place that should be too chaotic and too dense for anything new to form, especially a stable, massive object, yet it defied expectations and did exactly that. The conventional wisdom in astronomy has long held that such extreme environments are destructive rather than creative, that they tear things apart rather than building them up. But as we're learning, the universe is far more creative and surprising than our theories sometimes give it credit for. The process of gas stripping is known to be very efficient in head-on collisions, pushing huge amounts of material away from the main gravitational centers of the galaxies and into the intermediate space, which provides the necessary building materials for our mysterious object. This gas, once just fuel for stars, in the galaxies became the birthplace of a supermassive black hole. The transformation from star-forming material to black hole nursery required specific conditions that the collision provided. Extreme density, extreme pressure, and extreme turbulence all concentrated in a single region. These conditions would prove to be the perfect recipe for creating one of the most massive and mysterious objects in the universe, in a place where it had absolutely no business existing. The stage was set for a cosmic revelation that would force astronomers to rethink their most fundamental assumptions about how black holes are born. To see this violent dance, we needed a revolutionary tool, one that could look beyond the typical cosmic smog and peer into the heart of the collision. For decades, the Hubble Space Telescope gave us amazing, beautiful views of the universe in visible light. Hubble, seeing the universe primarily in light that our eyes can perceive, was perfect for spotting stars and the grand, luminous structures of galaxies. Launched in 1990 and continuously upgraded over its decades of operation, Hubble transformed our understanding of the cosmos, revealing galaxies billions of light years away, capturing the births of stars in spectacular nebulae, and showing us the universe in unprecedented detail. But the Infinity Galaxy is completely shrouded in dense, choking clouds of cosmic dust, especially in the most active central regions where the shockwaves are concentrated. Cosmic dust, despite its name, isn't like household dust at all. It consists of tiny particles, typically less than a micron across, made primarily of carbon and silicate materials. These particles are incredibly efficient at absorbing and scattering visible light, which is why dense dust clouds appear as dark patches in optical images. Dust is like a thick, opaque curtain that completely blocks visible light, hiding the most energetic parts of the collision from Hubble's view. When you look at the center of the Infinity Galaxy with visible light, all you see is a dark, impenetrable cloud, a blackness that hides the immense cosmic violence within. This limitation isn't unique to the Infinity Galaxy. It's a challenge that astronomers face throughout the universe. Some of the most interesting and energetic processes in the cosmos occur in dusty regions. Star formation happens inside dense molecular clouds. The centers of galaxies are often obscured by dust, and the most active regions of colliding galaxies are invariably the dustiest. For decades, these regions remained frustratingly mysterious, visible only through indirect means or at wavelengths beyond the visible spectrum. Hubble could show us the outer structure and some regions of star formation, but the true heart of the collision, where the most extreme physics was occurring, remained hidden. Enter the James Webb Space Telescope. Webb is an infrared specialist, meaning it sees light that has a longer wavelength than what our eyes can see, light that we primarily feel as heat. This longer wavelength light has the incredible ability to pierce right through those thick dust clouds, revealing the hidden fireworks show beneath. It's like switching from your eyes to a thermal camera that can see through walls. Infrared light, with its longer wavelengths, interacts differently with dust than visible light does. While visible light gets scattered and absorbed by dust particles, infrared light, especially longer wavelength infrared, passes through dust relatively unimpeded, allowing us to see regions that are completely invisible at optical wavelengths. Specifically, Webb's mid-infrared instrument, or MIRI, was absolutely essential for this discovery. MIRI is a marvel of engineering, cooled down to an astonishing negative 447 degrees Fahrenheit, or 7 degrees above absolute zero, to maximize its sensitivity, allowing it to pick up the faintest signals of heat and chemical signatures from billions of light years away. This extreme cooling is necessary because even the telescope itself would emit more infrared light than the distant object if it were warm. At room temperature, objects glow brightly in the infrared, which would overwhelm the faint signals from distant cosmic sources. By cooling MIRI to within a few degrees of absolute zero, engineers eliminated this background glow, allowing the instrument to detect incredibly faint infrared emissions from the most distant and obscured objects in the universe. The engineering required to achieve and maintain this temperature in space is extraordinary. MIRI uses a dedicated cryocooler system, essentially a sophisticated refrigerator, to actively cool its detectors to this incredibly low temperature. The rest of the Webb telescope is kept cool passively by its enormous sunshield, a 5-layer structure the size of a tennis court that blocks heat and light from the sun, earth, and moon. But MIRI needed even more cooling, requiring this active refrigeration system to reach its operational temperature. The result is an instrument of unprecedented sensitivity in the mid-infrared, capable of detecting thermal emissions that would be completely invisible to any previous telescope. The sunshield itself is an engineering marvel worth understanding. Each of its 5 layers is made of a material called capton, coated with aluminum, and on the sun-facing layers, doped silicon for additional reflectivity. The layers are separated by gaps, and each successive layer is cooler than the one before it. The sun-facing layer can reach temperatures of around 230 degrees Fahrenheit, while the layer closest to the telescope is a frigid, negative 390 degrees Fahrenheit or colder. This temperature gradient across just a few feet of space is achieved through careful engineering of the spacing, reflectivity, and emissivity of each layer. The sunshield must always be positioned between the telescope and the sun, which is why Webb orbits at a special location called the second Lagrange point, or L2, about 1 million miles from Earth on the side opposite the sun. At this location, Webb can keep its sunshield pointed at the sun, Earth, and moon simultaneously, all of which appear very close together in the sky from that vantage point while pointing its telescope toward deep space. This positioning is crucial for maintaining the cold temperatures needed for infrared observations. But back to MIRI specifically, the cryocooler that keeps MIRI cold is itself a technological achievement. It uses helium gas in a closed loop, compressing and expanding it in a carefully controlled cycle that extracts heat from the detectors. The cooler has to operate in the vacuum of space, has to be incredibly reliable with no possibility of repair for the lifetime of the mission, and has to produce minimal vibration that could blur images. Engineers spent years developing and testing the system to ensure it would work flawlessly. The detectors inside MIRI are arsenic-doped silicon detector arrays, specifically designed to be sensitive to mid-infrared light in the wavelength range of 5 to 28 microns. For comparison, visible light has wavelengths of about 4 to 7 microns, so MIRI is looking at light with wavelengths 10 to 50 times longer than what our eyes can see. At these wavelengths, warm objects glow brightly, which is why MIRI had to be so cold. Any warmth in the detectors themselves would create overwhelming background noise. MIRI is tuned to detect the faint, warm glow of complex chemicals and heated gas. For instance, it spots polycyclic aromatic hydrocarbons, or PAHs. These are large, complex carbon molecules, a sort of cosmic soot, that glow brightly when they are excited by intense energy. PAHs are everywhere in the universe, formed when starlight or energetic processes interact with dust. They're actually similar to some molecules found in Earth's atmosphere from combustion processes, but on a cosmic scale. These molecules have distinctive emission features in the infrared spectrum, creating a sort of fingerprint that MIRI can detect and measure. PAHs are often seen around regions of massive star formation, or crucially, around a feeding black hole, where the immense radiation excites them and causes them to emit brightly in the infrared. The energy from young, hot stars or from the accretion disk around a black hole pumps energy into these molecules, causing them to vibrate and eventually release that energy as infrared photons. By mapping the location of pH emissions, astronomers can map the areas where gas is being vigorously heated and energized. It's like having a cosmic thermometer and energy detector rolled into one, showing not just where things are, but how energetic they are and what kinds of processes are occurring. MIRI also easily detects the light from ionized hydrogen gas, which we discussed as hydrogen atoms that have had their single electron stripped away, leaving a bare proton. This ionization process takes enormous energy that can only come from shock waves, intense young stars, or the immense gravity of a black hole heating an accretion disk. When ionized hydrogen recombines with electrons, it emits light at specific wavelengths, creating emission lines that are characteristic signatures of ionized gas. MIRI can detect these lines in the infrared, allowing astronomers to map the distribution of ionized gas throughout the collision zone and measure its properties like temperature, density, and velocity. This ability to see through the dust and spot these chemical and heat signatures is what made Webb's discovery possible. It was like an X-ray machine for the cosmos, showing us the truth that had been invisible for 8 billion years. While Hubble saw beauty in the outer regions and captured stunning images of the collision's large-scale structure, it was essentially blind to the collision's most violent core. Webb changed everything, pulling back the cosmic curtain to reveal the true nature of what was happening in the heart of the infinity galaxy. Hubble could see the stars and the outer structure. Webb could see the gas and the extreme hidden energy sources deep inside the crash. By looking deeper into the heat and chemical signatures, the JWST team was able to map the exact locations of the most energetic processes in the entire colliding system. And what they found completely defied the maps they thought they knew. The standard model for colliding galaxies predicted that the most energetic regions would be at the galactic cores, where the central supermassive black holes resided, and in the stellar rings, where massive star formation was occurring. But Webb's maps showed something different, something unexpected. An enormous source of energy sitting in the void between the two galaxies, far from any galactic nucleus, glowing brilliantly in the infrared. The power of Webb lay not just in its ability to image in infrared, but in its ability to combine imaging with spectroscopy, which is the study of light broken down into its different colors or wavelengths. This technique is what allowed them to not just see the gas, but to measure its composition, its temperature, and most importantly for our story, its speed and direction. Spectroscopy works by spreading light out into its component wavelengths, like a prism splitting white light into a rainbow. But unlike a simple rainbow, astronomical spectra contain an enormous amount of information encoded in the exact wavelengths of light present or absent. When atoms and molecules emit or absorb light, they do so at very specific wavelengths determined by their quantum structure. Hydrogen, for example, emits light at specific wavelengths when its electrons move between energy levels. By measuring these wavelengths with extreme precision, astronomers can determine not just what elements are present, but also their temperature, density, and motion. If a source is moving toward or away from us, the Doppler effect shifts all these wavelengths slightly toward the blue or red end of the spectrum, allowing us to measure velocities with incredible accuracy. This spectroscopic capability would prove absolutely crucial for understanding the mysterious object in the void. When astronomers first analyzed the JWST data on the infinity galaxy, they operated under the assumption of the cosmic rulebook, the well-established understanding of galactic evolution that had been built up over decades of observations and theoretical work. They expected to find two active supermassive black holes, or SMBHs, one at the center of each original galaxy. This is because almost every large galaxy, including our own Milky Way, has one of these gravitational behemoths at its core, acting as the galaxy's gravitational anchor, the fixed point around which the galaxy rotates. The relationship between galaxies and their central black holes has been one of the major discoveries of modern astronomy. Observations over the past few decades have revealed that virtually every substantial galaxy hosts a supermassive black hole at its center, and moreover, the mass of this black hole is tightly correlated with properties of the galaxy itself, particularly the mass of the galaxy's central bulge. This suggests a deep connection between galaxy evolution and black hole growth, a co-evolution that has shaped the structure of the universe we see today. These two expected SMBHs would be the dominant sources of power, fueled by the gas settling into the inner regions of their host galaxies during the collision. What they saw was an instant shock, the kind of discovery that makes a scientist jump out of their chair and recheck their instruments, looking for any possible mistake or error in the data processing. Yes, there were two distinct, powerful energy sources in the expected galactic centers, confirming the presence of the anticipated supermassive black holes. But the brightest, most powerful source of energy was nowhere near either one. Instead, it was found exactly in the wide-open void, the deep space between the two colliding galactic centers. This wasn't where anything was supposed to be, least of all the most energetic object. In the entire system, this was not a small, faint glow that could be easily dismissed or attributed to some minor astrophysical process. It was a beacon of high-energy light, shining brilliantly across multiple wavelengths of the electromagnetic spectrum. The intense emission of X-rays measured by orbiting X-ray telescopes like Chandra, radio waves, detected by powerful ground-based radio observatories such as the Very Large Array, and the strong light from highly ionized atoms picked up by JWST's MIRI, was undeniable, powerful evidence of an active, feeding black hole. Each of these different wavelengths told part of the story, and together they painted an unmistakable picture. This specific signature of high-energy light only comes from the incredible gravity of a black hole pulling in and superheating surrounding matter into an accretion disk. X-rays come from gas heated to tens of millions of degrees in the innermost regions of the accretion disk, where matter is spiraling toward its doom at nearly the speed of light. Radio waves come from jets of particles launched perpendicular to the disk at relativistic speeds, creating powerful synchrotron radiation. The ionized atomic emission lines detected by MIRI come from slightly cooler regions where gas is still being heated and accelerated but hasn't yet reached the extreme temperatures of the inner disk. The combined evidence across the electromagnetic spectrum painted a clear picture of a gargantuan energy source far from any galactic nucleus, situated right in the messy, energetic zone of the collision shockwaves. This multi-wavelength approach is crucial in modern astronomy because different processes emit light at different wavelengths. By observing the same object across the entire electromagnetic spectrum, from radio waves to gamma rays, astronomers can piece together a complete picture of what's happening. In this case, every wavelength pointed to the same conclusion. There was a supermassive black hole actively feeding in the intergalactic void. The strange object they found was a cosmic outlier, a true phantom in the void, something that shouldn't exist according to the standard models of galaxy evolution and black hole formation. It was not a small black hole, not some stellar mass remnant that could have wandered into the collision zone. It was a fully fledged supermassive black hole, an SMBH, with a mass estimated to be around 1 million times the mass of the Sun. To put that in perspective, the black hole in our own galaxy, Sagittarius A star, or SGRAA, as astronomers write it, is about 4 million solar masses, and it anchors our entire Milky Way galaxy, which contains hundreds of billions of stars. This new black hole is not a minor player. It's a massive gravitational engine, a gravitational anchor in its own right, just without a galaxy to anchor. With a mass of 1 million suns, this object has a gravitational influence that extends across thousands of light years, affecting the motion of gas and stars throughout the collision zone. And it was sitting squarely in the middle of a vast cloud of glowing, stripped hydrogen gas. This gas was the material that had been violently compressed and swept up by the galaxy collision, the superheated debris in the intergalactic medium. It was this compressed material that the black hole was actively eating, making it shine so brightly for Webb and other telescopes to detect. The black hole was actively consuming this gas at an incredibly high rate, which is the key to its immense luminosity. When we say a black hole is active or feeding, we mean it's actively accreting matter from its surroundings. The rate of accretion determines how bright the black hole appears to us. A black hole sitting in empty space is completely invisible, emitting no light whatsoever. But a black hole surrounded by a rich supply of gas and dust becomes one of the brightest objects in the universe, potentially outshining entire galaxies. The brightness we observe is directly related to how much matter is falling into the black hole per unit time. This black hole wasn't just dormant or quietly sitting there, it was active, a characteristic that is absolutely vital to the story. Active means it was surrounded by a sizzling, swirling ring of gas and dust called an accretion disk. This disk forms because matter can't fall directly into the black hole. Conservation of angular momentum forces it to spiral inward, forming a rotating disk. As matter in this disk spirals inward, drawn by the black hole's gravity, it gets compressed and heats up to millions of degrees from friction and gravity, far hotter than the surface of any star. The inner regions of the accretion disk, closest to the black hole's event horizon, reach temperatures of tens of millions of degrees, hot enough to emit X-rays. The middle regions, slightly cooler at a few million degrees, emit ultraviolet light. The outer regions, merely tens of thousands of degrees, emit visible and infrared light. This intense heat releases a massive amount of high-energy light across the spectrum, from radio waves to X-rays, that provided the clear observational signatures. The luminosity from an actively feeding supermassive black hole can exceed 10 trillion times the luminosity of our Sun, making these objects visible across cosmological distances. The sheer magnitude of the light coming from this central void made it an absolute certainty. Something enormous and powerful was happening right where the textbook said nothing was supposed to be. The estimated accretion rate, the rate at which the black hole is consuming matter, was extremely high, further proving its massive energy output and confirming its supermassive nature. Astronomers calculated that the black hole was consuming roughly the equivalent of one sun's worth of mass every few years, a staggering rate of consumption that was necessary to produce the observed luminosity. The mystery only deepened when the astronomers fully analyzed the entire system across multiple wavelengths of light. The Infinity Galaxy doesn't just host two black holes, the usual suspects in the galactic cores. It actually hosts three active black holes, the strange one in the middle, and one in each of the two original galactic nuclei. This unprecedented finding is what scientists call the triple threat, a cosmic configuration that had never been observed before in such detail. To find even two supermassive black holes active at the same time in a colliding system is rare enough. Most of the time, when galaxies collide, the central black holes are obscured by thick dust, or one black hole's immense power simply shuts off the activity of the other through a process known as quasar feedback, where the energy output from one active black hole pushes away the gas that would otherwise feed the other. The radiation pressure from an extremely luminous black hole can effectively blow away gas not just from its immediate surroundings, but from a large region of the surrounding galaxy or collision zone. This feedback process is thought to be crucial in regulating black hole growth and galaxy evolution. To find three active black holes, with the third one residing in the intergalactic medium, the space between the galaxies, is completely unprecedented. The rarity of this triple SMBH configuration cannot be overstated. It is a 1 in a million find that suggests the collision was a catalyst for extreme gravitational activity. The collision didn't just disturb the existing black holes, it somehow created conditions favorable for all three to be actively feeding simultaneously. A remarkable state that suggests an abundance of available gas and specific geometric arrangements that allowed matter to reach all three objects. It suggests that the collision didn't just smash things. Together, it catalyzed the creation or activation of black holes in a way astronomers hadn't fully imagined. It is a chaotic, three-body gravitational engine of cosmic extremes, a temporary configuration that is destined for a violent final merger. Three-body gravitational systems are notoriously chaotic and unstable. Unlike two-body systems, which follow predictable orbital patterns, three-body systems can exhibit wildly unpredictable behavior, with orbits that change dramatically over time. This system cannot remain in its current configuration indefinitely. Eventually, the three black holes will interact, merge, or one will be ejected from the system entirely. The two SMBHs in the galactic cores are what we expect. The standard, ancient gravitational anchors for their host galaxies, likely billions of solar masses in size. Based on the size and luminosity of the two galaxies, astronomers estimate that each galactic nucleus hosts a black hole with a mass between 100 million and 1 billion times that of the Sun. These are mature, well-established black holes that have likely been growing for billions of years, accumulating mass through steady accretion and occasional mergers with smaller black holes. But the third one, the one in the void, that's the smoking gun, the piece of evidence that turns all the standard textbooks upside down. Its very existence in that location becomes the core conflict of our story. The question is no longer just what it is, but where it came from and how it got so big, so fast, in a place that has no galaxy nucleus to call home. With a mass of 1 million solar masses, this object is clearly supermassive by definition, yet it sits in intergalactic space with no obvious parent galaxy. This presents a profound puzzle that strikes at the heart of our understanding of black hole formation. This object is not merely a supermassive black hole, it is a naked black hole, stripped of its galactic host, or perhaps a newborn black hole formed in the most unlikely of nurseries. These two possibilities represent fundamentally different scenarios with dramatically different implications for our understanding of the universe. If it's a naked black hole ejected from one of the galaxies, that would be interesting but not revolutionary. Such ejections are theoretically possible, though rarely observed. But if it's a newborn black hole formed in situ in the intergalactic void, that would be genuinely revolutionary, requiring us to completely rethink how supermassive black holes can form. The existence of a 1 million solar mass black hole floating free in the gas between two galaxies challenges the most fundamental ideas about how these objects are born, forcing us to explore the great controversy in modern astronomy. To understand the conflict, we have to talk about the two main theories of black hole birth, the two competing ideas for how the universe creates its most massive objects. This debate has been ongoing for decades and has intensified dramatically with observations from the James Webb Space Telescope revealing supermassive black holes in the early universe that seem impossibly large for their age. The first and historically most dominant idea for the last few decades is the light seed theory. This is the standard story of stellar life and death that we teach in classrooms, a well-understood process that astronomers have observed countless times throughout the universe. It starts with the biggest, most enormous stars in the universe. These are the stars that might be 100 or even 200 times the mass of our sun, called massive stars. Stars of this size are rare in today's universe, but would have been somewhat more common in the early cosmos when conditions were different. These massive stars are not long-lived. They burn through their nuclear fuel at an alarming rate, living fast and dying young, often in just a few million years. A star like our sun, with just one solar mass, will live for about 10 billion years, peacefully fusing hydrogen into helium in its core for most of that time. But a star with 100 solar masses lives for perhaps only 3 million years, burning so hot and so bright that it exhausts its fuel reserves in a cosmic blink of an eye. These stars are profligate consumers of fuel, fusing not just hydrogen, but progressing through heavier and heavier elements in their cores: helium, carbon, oxygen, neon, magnesium, silicon, and finally iron. When they run out of fuel, their core collapses in a catastrophic explosion called a supernova, spreading heavy elements across the cosmos. The iron core, unable to generate more energy through fusion, collapses under its own gravity in a fraction of a second. The outer layers of the star, rebounding off the collapsing core, are blown outward in a spectacular explosion that can briefly outshine an entire galaxy. This explosion enriches the surrounding space with heavy elements, seeding future generations of stars and planets with the chemical building blocks of complexity. The supernova process itself is one of the most violent events in the universe, and understanding it helps us appreciate why stellar mass black holes are typically so small. When the iron core of a massive star collapses, it compresses from roughly the size of Earth down to about 10 kilometers in radius in less than a second. The density becomes so extreme that protons and electrons are forced to combine into neutrons, releasing an enormous flux of neutrinos. These ghostly particles, which barely interact with matter, carry away the vast majority of the energy from the collapse, about 99% of it. The visible light and kinetic energy of the explosion represent just 1% of the total energy released. As the core collapses, it may halt at neutron star densities if the core mass is below about 3 solar masses. Neutron star matter is so dense that a teaspoon of it would weigh 1 billion tons on Earth. The pressure from neutron degeneracy, a quantum mechanical effect where neutrons resist being squeezed too close together, can halt the collapse, creating a stable neutron star. But if the core is more massive than about 3 solar masses, even neutron degeneracy pressure cannot stop the collapse. The core continues shrinking, passing through the point of no return, the event horizon, and a black hole is born. Crucially, much of the star's original mass is blown away in the supernova explosion, not retained in the remnant. A 25 solar mass star might leave behind only a 3 solar mass black hole, with the remaining 22 solar masses dispersed into space. This mass loss during the supernova is one of the reasons why stellar mass black holes are limited in size. Even the most massive stars we've ever observed, with initial masses up to perhaps 200 solar masses, are unlikely to leave behind black holes more massive than about 50 solar masses, and most stellar black holes are in the range of 5 to 20 solar masses. This size limitation is fundamental to the light seed problem. If stellar processes can only produce black holes of 5 to 50 solar masses, and we need to grow these seeds to millions or billions of solar masses, we need enormous growth factors and enormous amounts of time. A stellar black hole of 10 solar masses needs to grow by a factor of 100 million to reach a billion solar masses. That's a staggering amount of growth, and as we'll see, the physics of accretion limits how fast this growth can occur. If the star's core is incredibly dense and heavy enough after the explosion, it doesn't just turn into a neutron star, it collapses all the way down to a small, compact black hole. The threshold is around 25-30 solar masses for the original star. If the core remaining after the supernova is more than about 3 solar masses, not even neutron degeneracy pressure can stop the collapse, and a black hole forms. These are the light seeds, typically only 10 to 100 times the mass of the Sun. The key word here is small. These are the starting blocks, the remnants of singular, massive stars, the smallest category of black holes that can form through stellar evolution. The light seed theory then says that these small seeds, over the course of cosmic history, grow into the giant supermassive black holes we see today through 2 very slow and patient processes that take billions of years. The first is accretion, which is simply the black hole eating surrounding gas and dust slowly, gaining weight bit by bit over millions of years. As the black hole moves through space, or as gas flows past it, some of that material gets captured by the black hole's gravity and gradually spirals inward, adding to the black hole's mass. This process sounds straightforward, but there's a critical limitation. The rate at which a black hole can eat is not unlimited. It's governed by a crucial physical principle called the Eddington limit, one of the most important concepts in understanding black hole growth. This limit is named after the famous astronomer Arthur Eddington, who first derived it in the context of stellar luminosity, but which applies equally to black holes. It says that as a black hole eats, the gas is heated up to incredible temperatures, releasing massive amounts of light and radiation. This powerful radiation pressure pushes outwards against the infalling gas, essentially limiting how fast the black hole can grow. It's a cosmic traffic jam where the light is pushing the food away. The faster the black hole tries to eat, the more light it generates, and the more that light pushes the food away. This creates a natural speed limit on black hole growth. Mathematically, the Eddington limit tells us that a black hole of a given mass can only accrete matter at a certain maximum rate before the radiation pressure from the accretion process prevents additional matter from falling in. For a stellar mass black hole of 10 solar masses, this translates to a maximum growth rate of doubling its mass every few tens of millions of years, assuming it has an unlimited supply of gas. Let's dive deeper into why the Eddington limit exists and why it's so important. When matter falls toward a black hole, gravitational potential energy is converted to kinetic energy. The matter speeds up. But matter can't fall directly into the black hole because of angular momentum conservation. Instead, it forms a swirling accretion disk. Within this disk, friction between adjacent layers of material converts kinetic energy into heat, causing the disk to glow. The innermost regions of the disk, where the orbital velocities are highest and the friction is most intense, become extremely hot, millions of degrees, and radiate primarily in the X-ray part of the spectrum. This radiation isn't just escaping harmlessly into space, it's also pushing on the infalling material. Photons carry momentum, and when they strike electrons in the infalling gas, they transfer that momentum, exerting a force called radiation pressure. If the accretion rate becomes too high, the luminosity becomes too great, and the outward radiation pressure exceeds the inward gravitational force. At this point, matter is literally blown away from the black hole faster than it can fall in. This defines the Eddington limit, the maximum luminosity a black hole can sustain while still accreting matter. The Eddington luminosity scales with black hole mass. A more massive black hole has a higher Eddington luminosity, meaning it can be brighter while still accreting. But importantly, the maximum mass accretion rate also scales with mass, which means the fractional growth rate, how fast the black hole grows as a percentage of its current mass, stays roughly constant regardless of size. This is why we can define a characteristic exponential growth timescale, the salpeter time of about 45 million years, that applies to black holes of any mass accreting at the Eddington limit. However, there's a catch. Real black holes don't accrete at the Eddington limit continuously. The Eddington limit represents a theoretical maximum under idealized conditions, specifically assuming the accretion flow is spherically symmetric and the gas is fully ionized. In reality, accretion disks have complex geometries, magnetic fields play important roles, and gas isn't always available in unlimited quantities. Most black holes probably accrete well below the Eddington limit most of the time, with occasional bursts when gas becomes particularly abundant. Moreover, as black holes grow more massive and luminous, they begin to affect their environment on larger scales. The radiation and winds from a bright, active galactic nucleus can heat or expel gas from the surrounding galaxy, a process called AGN feedback. This self-regulation mechanism tends to limit how much a black hole can grow, keeping it in balance with its host galaxy. This is actually thought to be the origin of the tight correlations we observe between black hole masses and galaxy properties. The black hole grows until its feedback shuts off further growth, and this happens at a mass that's proportional to the galaxy's mass. All of these complications mean that the light seed model faces even more severe challenges than the simple Eddington limited accretion calculation suggests. Not only is there a hard physical limit on how fast black holes can grow, but in practice, they often grow much slower than this limit allows. This is the bottleneck of the light seed model. Even if a black hole has unlimited food available, the Eddington limit constrains how fast it can grow. And in practice, black holes rarely have unlimited food. Gas supplies are often limited, and feedback processes can shut off accretion entirely for long periods. This means that growing from a 10 solar mass seed to a billion solar mass supermassive black hole through accretion alone would take many billions of years, even under the most favorable circumstances. The second process is mergers, where these seeds slam into each other and combine their mass. When two black holes orbit each other closely enough, they emit gravitational waves, ripples in space-time that carry away energy and angular momentum from the system. This causes the orbit to gradually decay, bringing the black holes closer and closer together until they eventually merge in a violent collision that produces a single, larger black hole. This process also takes immense amounts of time, requiring close encounters and orbital decay over millions or billions of years. For two black holes to merge, they first need to encounter each other, which requires them to be in the same galaxy or for their host galaxies to merge. Then, through a process called dynamical friction, where the black holes interact gravitationally with surrounding stars and gas, they slowly spiral toward the center of the merged galaxy. Finally, when they're close enough, gravitational wave emission takes over and drives the final merger. The entire process from galaxy collision to final black hole merger can take billions of years. So, the light seed model is a slow, patient growth over millennia, a gradual process of feeding and combining, a process that requires billions of years to create a massive monster. It's the standard, widely accepted path for most supermassive black holes, and it works well for explaining the black holes we see in mature galaxies in the nearby universe. Our own Milky Way's black hole, SGR-A-Fu, likely grew through this slow process over the galaxy's lifetime. But as we're about to see, this model runs into serious problems when we look at the earliest epochs of cosmic history. But here's where the problem, the major controversy, arises, a controversy that JWST has only intensified. The James Webb Space Telescope, looking deep into the early universe, has found monstrously large supermassive black holes that are already billions of solar masses existing only a few 100 million years after the Big Bang. These observations have shaken the foundations of black hole formation theory and sparked intense debate in the astronomical community. Think about that timeline again. The universe is only about 8 billion years old. These gargantuan black holes existed when the universe was less than 1 billion years old, some as early as 400 or 500 million years after the Big Bang. We're observing these objects at redshifts of 7, 8, 9, or even higher, which corresponds to looking back to when the universe was in its infancy. At that time, the first stars had only recently formed, the first galaxies were just beginning to coalesce, and the universe was fundamentally different from what we see today. The light seed model requires billions of years of slow feeding and merging, limited by the Eddington rate. There simply wasn't enough time for a small seed to eat and merge its way up to 1 billion solar masses in just a few 100 million years. The numbers don't add up. It's mathematically impossible. Calculations show that even if a light seed black hole ate at the maximum possible rate, the Eddington limit, for the entire lifespan of the young universe, it still wouldn't be big enough by a factor of hundreds. Let's do the math to see why this is such a problem. If a 10 solar mass black hole accretes at the Eddington limit continuously, it can double its mass in about 45 million years. This is called the Salpeter time, named after astronomer Edwin Salpeter. Starting from 10 solar masses and doubling every 45 million years sounds impressive, but let's see where it gets us. After 450 million years, 10 doubling times, we'd have a black hole of about 10,000 solar masses. After 900 million years, we'd reach about 10 million solar masses. To reach 1 billion solar masses would require about 30 doublings, or about 35 billion years of continuous Eddington-limited accretion. But the observations show billion solar mass black holes at redshift 7 or 8, corresponding to only 700, 800 million years after the Big Bang. The math simply doesn't work, and that's assuming continuous accretion at the maximum possible rate with unlimited gas supply, which is an unrealistically optimistic scenario. In reality, black holes don't accrete continuously. There are interruptions when gas supplies are depleted or when feedback processes temporarily halt accretion. This makes the problem even worse. It's like trying to grow a mountain in a single afternoon. The mathematics of the slow growth model just don't work for the biggest, earliest black holes we are seeing. The light seed theory, while great for explaining black holes in the modern universe, runs into a major roadblock when we look back into the deepest history of the cosmos. Astronomers call this the early universe problem, or sometimes the impossibly massive black holes problem. This huge gap in understanding forced them to look for a more explosive, faster, and more efficient way to create the biggest black holes. The observations kept getting more puzzling. Webb found not just 1 or 2 early massive black holes, but many of them, suggesting this isn't just a rare fluke, but perhaps a common occurrence in the early universe. Some of these black holes are so massive and so early that they challenge not just the light seed model, but our understanding of how the early universe worked. If these objects can't form through stellar processes, then how did they form? This question led astronomers to seriously consider a radical alternative that had been proposed decades earlier but lacked observational support. This is where the controversial alternative comes in, the direct collapse hypothesis, sometimes called the heavy seed model. The idea here is revolutionary. Why start with a small 10 solar mass seed when you can start with something already enormous? This theory suggests that under extremely special conditions, a single, gigantic cloud of gas skips the whole star-making process and collapses directly into an SMBH. Instead of forming a star that later collapses to leave behind a small black hole, the entire cloud collapses at once, forming a massive black hole in one dramatic event. The estimated mass of this initial collapsing cloud would need to be in the range of 100,000 to 1,000,000 times the mass of the Sun. It collapses whole, creating a black hole that is already huge from day one. Imagine a gas cloud with the mass of 1,000,000 suns, all concentrated in a region perhaps only a few light years across, suddenly collapsing under its own gravity, directly to a black hole without ever fragmenting into stars. This is the promise of the direct collapse model. It gives you a massive black hole immediately, without having to wait billions of years for slow growth. These special conditions are crucial to the direct collapse model, and are the key to understanding why this process doesn't happen everywhere all the time. They usually mean the gas cloud must be almost entirely made of hydrogen and helium without any metal pollution. This requirement stems from the basic physics of gas cloud collapse and fragmentation. When a gas cloud starts to collapse under its own gravity, it heats up from compression. If it can efficiently radiate away this heat, it will cool down and cooler gas fragments more easily into smaller clumps. These smaller clumps then collapse individually to form stars. In astronomy, the term metals is used to describe any element heavier than hydrogen and helium, the two lightest and most common elements. This is a peculiar usage that often confuses non-astronomers, but it's standard terminology in the field. So when an astronomer says metal-rich or metal-poor, they're talking about the abundance of elements like carbon, oxygen, nitrogen, iron, and so on, relative to hydrogen and helium. Metals like carbon, oxygen, and iron are created inside stars and released when they explode in supernovae, or shed their outer layers as planetary nebulae. The reason metals are such efficient coolants is rooted in atomic and molecular physics. Atoms and molecules can absorb energy from collisions with other particles, storing that energy in the form of electronic excitation or vibrational and rotational motion. They then release this energy by emitting photons, which carry the energy away. The more energy levels an atom or molecule has available, the more efficiently it can radiate energy and cool the gas. Hydrogen and helium, being the simplest elements, have relatively few energy levels accessible at the temperatures typical of collapsing gas clouds. Molecular hydrogen can cool gas through rotational and vibrational transitions, but this becomes inefficient at temperatures above a few thousand degrees, where the molecules dissociate. Atomic hydrogen can cool through the Lyman alpha transition, but this requires temperatures of at least 10,000 degrees. In contrast, metals like carbon and oxygen have many electronic transitions accessible at lower temperatures, and metal-containing molecules like CO and water are excellent coolants over a wide range of temperatures. When a gas cloud enriched with metals begins to collapse, these cooling mechanisms kick in very efficiently. The gas radiates away, its thermal energy cools down, and as it cools, fragments into smaller clumps. Each clump continues collapsing and cooling independently, eventually forming individual stars. This fragmentation process is why molecular clouds in our galaxy produce not single massive objects, but clusters of stars with a range of masses, from tiny brown dwarfs to massive O and B stars. But in the absence of metals, this fragmentation is suppressed. Primordial gas clouds composed only of hydrogen and helium can't cool efficiently once they reach temperatures of a few thousand degrees. The gas remains relatively warm, and warm gas resists fragmentation because its thermal pressure counteracts gravity over small scales. The result is that the cloud can remain coherent over much larger masses, potentially accumulating hundreds of thousands or even millions of solar masses before conditions become right for collapse. When such a massive cloud finally does collapse, it can't form a normal star. Objects with masses much above about 100 solar masses are unstable due to radiation pressure. Their own light would blow them apart. Instead, the collapsing cloud passes through a phase where it becomes extremely dense and hot in the center, potentially triggering what's called a quasi-star, a bizarre object where a black hole forms at the center but is surrounded by a massive envelope of gas that continues to feed it. The end result after this brief quasi-star phase is a massive black hole with an initial mass in the 100,000 to 1 million solar mass range, a heavy seed that bypasses the entire slow growth problem of the light seed model. If the gas has these metals, it cools too efficiently by radiating away heat. The metal atoms and molecules are excellent coolants because they have many energy levels and can radiate energy away through electronic and vibrational transitions. When gas cools efficiently, it fragments and breaks up into smaller clumps, forming many small stars instead of one single giant cloud that can collapse whole. This fragmentation process is why star-forming regions typically produce not single stars, but clusters of stars with a range of masses. But if the gas is pristine, meaning it lacks these metals, like the gas present in the very early universe before the first stars had exploded, it can't cool efficiently. Pristine hydrogen and helium gas has far fewer ways to radiate energy compared to metal-enriched gas. It stays warm and resists fragmentation, creating a stable, massive structure that can only collapse under its own weight, thus forming a giant black hole. The gas cloud remains coherent, collapsing as a single entity rather than breaking up into star-forming fragments. Since the early universe was mostly pristine hydrogen and helium, this direct collapse model became the leading, albeit controversial, explanation for those impossibly large early black holes. The first generation of stars, called population 3 stars, formed from completely pristine gas and likely had very different properties from modern stars. After these first stars exploded as supernovae, they enriched their surroundings with metals. But there would have been a window of time and pockets of space where gas was still largely pristine, creating opportunities for direct collapse to occur. It's a cosmic shortcut, a way to have the gravitational monster born fully grown and ready to start eating. It bypasses the slow, Eddington-limited growth phase, solving the time problem. A direct collapse black hole starts at 100,000 or 1 million solar masses, already more massive than a stellar black hole could possibly be. From this head start, it only needs a few 100 million years of growth to reach the billion solar mass range we observe in the early universe. The math suddenly works out much better. This brings us back to the infinity galaxy and the core hypothesis, the sub-hook that connects this ancient theory to a modern collision. The black hole in the void of the infinity galaxy is a 1 million solar mass object. This is exactly the size predicted by the direct collapse model for the initial mass of a heavy seed black hole. This correspondence isn't proof by itself, but it's highly suggestive, and it is surrounded by a massive amount of incredibly compressed gas, the exact kind of high-density environment needed for a collapse. But here is the massive twist. This isn't primordial, pristine gas from the early universe. This is gas from two mature, metal-rich galaxies that are violently colliding. We're looking at a collision that occurred 8 billion years after the Big Bang, at a time when the universe was already mature and had been enriched with metals from multiple generations of stars. The gas in these galaxies has been processed through stars multiple times, enriched with carbon, oxygen, nitrogen, silicon, iron, and dozens of other heavy elements. If the gas is metal-rich, it should have cooled quickly and fragmented into millions of small stars, not collapsed into a single black hole. The presence of metals, which are excellent coolants, should have killed the possibility of direct collapse. This is the paradox that makes this discovery so profound. We're seeing what appears to be a direct collapse black hole forming from metal-rich gas, which shouldn't be possible according to our understanding of the physics. So how did the collapse happen? The proposed answer is a new collapse mechanism driven by the galaxy collision itself. The theory suggests that the immense, violent collision created the necessary, unique conditions to trigger a direct collapse in this metal-rich environment, despite the presence of cooling agents that should have prevented it. This is a radical proposal that sufficiently extreme conditions can override the normal cooling and fragmentation processes, forcing even metal-enriched gas to collapse as a single unit. The shockwaves caused by the galactic crash resulted in extreme gas compression and turbulence. This compression was so extreme that it created an environment with incredibly high pressure and high density, far beyond what's normally found in even the densest molecular clouds. Think of a cosmic vice grip, squeezing the gas with unimaginable force to densities far exceeding the typical conditions in a galaxy. In a normal galaxy, even the densest molecular clouds have densities of perhaps a few thousand or million hydrogen molecules per cubic centimeter. But in the collision zone, shockwave compression could create densities hundreds or thousands of times higher. Crucially, the immense pressure and the heat generated by the shockwaves somehow suppress star formation, overcoming the presence of metals. The high temperature generated by the collision, coupled with the crushing pressure, prevented the gas from cooling and fragmenting into smaller star-forming clumps. This is the key insight. Even though metals were present and should have cooled the gas, the extreme dynamics of the shockwave raised the temperature of the gas to a point where the main cooling agents primarily molecular hydrogen and metal-bearing molecules, were destroyed or rendered ineffective. At temperatures above a few thousand degrees, molecular hydrogen dissociates into atomic hydrogen, which is a much less efficient coolant. At even higher temperatures, atoms become ionized, losing their electrons and further reducing cooling efficiency. The shockwave essentially overheated the gas, raising it to such high temperatures that normal cooling mechanisms couldn't keep up. Meanwhile, the extreme pressure kept the gas from expanding, maintaining high density despite the high temperature. This meant the gas cloud was forced to remain a single, massive, stable structure. With cooling suppressed and pressure maintaining high density, the cloud couldn't fragment. It remained coherent, a single, massive entity held together by gravity. The result was a massive cloud of gas, millions of solar masses heavy, that couldn't form stars, couldn't cool fast, enough to break up, and ultimately had no choice but to collapse under its own gravity directly into a 1 million solar mass supermassive black hole. This is a dynamic pathway for direct collapse, not the slow, ancient way that required pristine gas. The collision was the trigger, the cosmic match that lit the fuse for a newborn black hole, creating an object that shouldn't exist in that time or place. It is a brand new chapter in the story of black hole birth, one that says these monsters can be created right now, today, in the heart of a cosmic crash, simply by forcing the environment to be extreme enough. The gas cloud was crushed into black hole status, a process that is both rare and incredibly violent. This mechanism has profound implications. It suggests that direct collapse isn't limited to the pristine gas of the early universe, but can occur anywhere conditions are extreme enough. Galaxy collisions, with their powerful shockwaves and extreme compression, might be factories for producing supermassive black holes throughout cosmic history. This could help explain not just the early black holes that JWST has found, but also provide a pathway for producing supermassive black holes in the more recent universe. Before the scientific community could accept this revolutionary idea of a collision-induced direct collapse, scientists had to follow the most important step in all of science, eliminating the competing explanations. This is the heart of the scientific method, the moment of confrontation that proves the theory is stronger than all the alternatives. In science, it's not enough to have a theory that explains the observations. You must also show that alternative explanations don't work. This process of elimination is what separates robust scientific conclusions from speculation. They had two main alternative scenarios to rule out, each of which could potentially explain the observations without requiring the radical idea of collision-induced direct collapse. The first was that the object wasn't born there at all. It was a runaway black hole ejected from one of the two galactic nuclei. In a chaotic triple-body gravitational system, like the 3 black holes we've found, it's possible for a complex gravitational interaction, a sort of cosmic slingshot, to violently fling one of the existing SMBHs out into the void at high speed. This ejection can happen if 2 black holes merge, and the resulting gravitational waves are emitted unevenly, giving the newly merged black hole a powerful kick. This is also known as a recoiling black hole. When 2 black holes merge, they produce gravitational waves, and if the system has certain asymmetries, those waves can carry away momentum preferentially in one direction, giving the merged black hole a kick in the opposite direction, like the recoil of a gun. These kicks can be quite powerful, reaching velocities of thousands of kilometers per second, potentially enough to eject the black hole from its host galaxy entirely. If this were the case, the black hole would simply be a visitor, not a newborn, and the discovery would be interesting but not revolutionary. It would just be a black hole that got evicted from its home galaxy and was now passing through the crash zone. A runaway black hole would be moving at hundreds or even thousands of kilometers per second relative to the gas, and it would show clear signs of this motion in its spectroscopic signature. The second possibility was that the black hole wasn't related to the infinity galaxy collision at all. It could be an unrelated black hole from a background galaxy that just happens to be coincidentally aligned on our line of sight. Given the immense distance of 8 billion light-years, a black hole from an even farther away galaxy, perhaps 10 or 12 billion light-years away, could appear to be floating between the 2 closer galaxies when viewed from Earth. This is called a projection effect, a trick of perspective, and it is a common headache for astronomers. The universe is three-dimensional, but we observe it projected onto the two-dimensional sky, which means objects at very different distances can appear close together. Determining whether objects that appear near each other on the sky are actually physically associated requires careful measurements of their distances and velocities. If either of these alternatives were true, the revolutionary idea of a collision-induced direct collapse would be wrong. The stakes for the team were incredibly high, and they needed a definitive measurement that could determine the object's true distance and motion. This is where the power of spectroscopy becomes absolutely crucial. To figure out the truth, the scientists turned to the spectroscopic showdown, the most crucial test in their arsenal. They needed to precisely measure the velocity of the mysterious object and compare it to the velocity of its surroundings. The velocity of an object in space tells you exactly how fast it is moving toward us, or away from us. This measurement is done through a concept called redshift, which is the stretching of light waves as the source moves away from us due to the expansion of the universe. As the universe expands, the space between distant objects stretches, and this stretching also affects the light traveling through that space, shifting it toward longer, redder wavelengths. The more stretched the light shifted toward the red end of the spectrum, hence redshift, the faster and farther away the object is. Redshift is typically denoted by the symbol Z, and it's directly related to the scale factor of the universe at the time the light was emitted. A redshift of 1 means the universe has doubled in size since the light was emitted. The Infinity Galaxy, at 8 billion light-years away, has a redshift of approximately Z1, meaning the universe was about half its current size when the light we're now seeing left those galaxies. Precise redshift measurements can tell us not only how far away an object is, but also, by looking for small differences in redshift between different parts of an object or between different objects, we can measure their relative velocities. The mathematics of redshift is elegant and revealing. When we measure the wavelength of a known spectral line, say the hydrogen alpha line, which has a laboratory wavelength of 656, 3 nanometers, and find it shifted to a longer wavelength in our observations, we can calculate the redshift using a simple formula: Z chargen, observed wavelength, rest wavelength, Dirk rest wavelength, if we observe the hydrogen alpha line at 1312. 6 nanometers, exactly twice its laboratory wavelength, then Z-1. This tells us both the distance to the object and, through the cosmological models, the time in cosmic history when the light was emitted. But redshift measurements can reveal more than just distance. If an object has internal motions, gas swirling around a black hole, stars orbiting in a galaxy, clouds of gas expanding from an explosion, these motions will cause slight variations in the redshift across the object. Gas moving toward us will be slightly less redshifted or even blue shifted compared to the average, while gas moving away will be more redshifted. By mapping these variations across the object, astronomers can create velocity maps that reveal the internal dynamics of distant cosmic structures. In the case of the Infinity Galaxy, the astronomers use spectroscopy to measure the exact redshift of multiple components: the 2 galactic nuclei, the ionized gas in the intergalactic medium, and the emissions from the mysterious black hole itself. Each measurement required carefully identifying spectral lines, signatures of specific atoms or ions, and measuring their wavelengths with high precision. Modern spectrographs can measure wavelengths to accuracies of better than 1 part in 10,000, which translates to velocity measurements accurate to tens of kilometers per second, even for objects billions of light-years away. The process isn't always straightforward. Spectra from distant galaxies are often messy, with multiple overlapping emission and absorption lines from different sources. There's the continuum emission from stars, emission lines from ionized gas in star-forming regions, absorption lines from stars' atmospheres, and emission from active galactic nuclei if present. Disentangling all these components requires sophisticated analysis techniques and careful modeling. In the case of the Infinity Galaxy, the astronomers had to separate the emission from the 3 different black holes, the surrounding ionized gas, and the star-forming regions, all while accounting for dust absorption that affects different wavelengths differently. The precision of their measurements was crucial for distinguishing between The competing hypotheses. If the mysterious black hole in the void were a runaway ejected from one of the galactic nuclei, it would be moving at high speed relative to the surrounding gas, perhaps 500 to 2,000 kilometers per second. This would produce a clear velocity offset between the black hole's emission lines and the gas emission lines, easily detectable with modern spectroscopy. Similarly, if the object were a background galaxy at a different distance, its redshift would differ from the infinity galaxy's redshift by an amount corresponding to its different distance. The fact that no such offsets were detected within the measurement uncertainties of a few tens of kilometers per second provided strong evidence that the black hole was indeed part of the collision system and moving with the gas. The black hole itself doesn't emit light, but the gas swirling into it, the accretion disk, does. So they used extremely precise radio and X-ray data to measure the velocity of the black hole's emission. The X-ray and radio emissions, produced by the most energetic parts of the accretion disk, have distinct spectral lines that can be measured for their redshift. These spectral lines come from specific atomic transitions or processes that occur at well-known wavelengths in the lab. By measuring how much these wavelengths have shifted in the observations, astronomers can determine the velocity. Then they use JWST spectroscopy, specifically the MIRI data we talked about earlier, to measure the velocity of the surrounding ionized hydrogen gas cloud. This spectroscopic data is incredibly detailed. It breaks down the light into its constituent colors, allowing scientists to pinpoint the tiny shifts in the light's wavelength that tell them the exact speed of the gas cloud. MIRI's spectrographs can measure wavelengths with extraordinary precision, detecting shifts corresponding to velocities of just a few kilometers per second. The ionized hydrogen emits light at specific wavelengths, particularly the hydrogen alpha line and other transitions. By measuring the exact wavelength of these emission lines and comparing them to their known laboratory wavelengths, astronomers can calculate the redshift and thus the velocity of the gas. This test was the ultimate check on the black hole's origin and position. If the black hole were a runaway, its velocity would be significantly different from the gas cloud it was passing through, showing a velocity offset of hundreds or thousands of kilometers per second. If it were a background object, its redshift would be much higher than the two colliding galaxies. A galaxy at 12 billion light-years distance would have a redshift of about zeta Tus, 5 significantly different from zebra 1, and this difference would be immediately apparent in the spectroscopic measurements. The key finding was the absolute confirmation of the location, which supported the direct collapse hypothesis. The scientists found that the black hole's velocity matched the gas perfectly. The speed of the feeding black hole, measured from its X-ray and radio emissions, was exactly the same as the speed of the huge, million solar mass gas cloud surrounding it, measured by the ionized hydrogen lines in the JWST spectrum. Within the measurement uncertainties, which were quite small, there was no detectable velocity difference. The difference in their measured velocities was essentially zero, meaning they were moving together as a single unit. This result confirms that the black hole is kinematically linked to the surrounding gas. Kinematically linked is astronomy, jargon meaning moving together, indicating that the two objects are gravitationally bound and part of the same system. It's not a runaway object speeding away from its parent galaxy, which would show a huge difference in velocity. A runaway black hole ejected at even a modest velocity of 500 kilometers per second would show a clear velocity offset that would be easily detectable in the spectroscopy. No such offset was observed. It's moving with a gas cloud, meaning it's gravitationally bound to it, born inside it. The black hole and the gas cloud are moving together through space, caught up in the complex gravitational dance of the colliding galaxies, but with no relative motion between them. This strongly suggests they formed together, or that the black hole has been embedded in this gas cloud for long enough that their velocities have equilibrated, but given the short timescales involved in galaxy collisions and the large mass of the black hole, the most likely explanation is that they formed together. Furthermore, this result also completely rules out the unrelated background galaxy idea. If it were an unrelated background object, its velocity, measured by its redshift, would have been significantly different, much higher, because it would be farther away and thus moving away from us faster due to the universe's expansion. The redshift measurements from all three black holes the two in the galactic nuclei and the one in the void, were consistent with all three being at the same distance from us, all part of the same colliding system at Z1. The finding essentially says this black hole was not just visiting that gas cloud, it was born there, and it lives there, moving in perfect sync with the massive cloud of gas it is currently consuming. This confirmed that the galaxy collision was the true catalyst, the cosmic engineer that created this new, impossible black hole. The combination of the velocity match, the correct redshift, and the physical association with the compressed gas cloud formed an airtight case that this was indeed a newborn black hole formed in situ in the intergalactic void. The challenge to the standard model of cosmic birth was now official, backed up by solid, undeniable, and repeatable spectroscopic evidence. Other teams could verify these measurements, could point their own telescopes at the infinity galaxy, and confirm the findings. This is a crucial aspect of scientific discovery. Results must be reproducible and verifiable by independent observers. The data from JWST, Chandra, and the VLA were all consistent, painting a coherent picture across multiple wavelengths and multiple independent observations. This single observation, this black hole born in the void of the infinity galaxy, has vast and deep implications for how we understand the history of the cosmos and the life cycle of galaxies. It forces us to fundamentally rethink the entire relationship between supermassive black holes and the galaxies that host them. For decades, the leading idea was black hole and galaxy co-evolution, a paradigm that has dominated our thinking about galaxy formation and evolution since the early 2000s. This theory states that a galaxy and its central black hole are intimately linked. They grow up together, constantly influencing each other in a complex dance. The discovery of tight correlations between black hole mass and galaxy properties, particularly the mass of the galaxy's bulge and the velocity dispersion of stars in the bulge, suggested a deep connection. These correlations are too tight to be coincidental. They imply that black holes and galaxies somehow regulate each other's growth. The black hole's energy can heat and push away gas, limiting star formation in the galaxy, a process called feedback. When a supermassive black hole is actively feeding, it can generate enormous amounts of energy, sometimes outshining the entire rest of the galaxy. This energy, in the form of radiation pressure, powerful winds, and jets, can blow gas out of the galaxy or heat it to such high temperatures that it can't collapse to form stars. This feedback is thought to be crucial in explaining why the most massive galaxies stop forming stars and become red and dead elliptical galaxies. The feedback process operates through several different mechanisms, each important at different scales. On small scales near the black hole itself, radiation pressure from the intense light of the accretion disk can drive powerful winds that blow gas away at thousands of kilometers per second. These winds, carrying mass away from the nucleus at rates comparable to the accretion rate onto the black hole, can clear out gas from the central few hundred light years of the galaxy, starving both the black hole and the surrounding star-forming regions. On larger scales, many actively feeding black holes launch jets. Narrow beams of particles accelerated to near the speed of light and shot out perpendicular to the accretion disk. The mechanism that produces these jets is still not fully understood, but it involves magnetic fields twisted by the rotating matter in the disk and near the black hole. These jets can extend for millions of light years, far beyond the host galaxy, depositing enormous amounts of energy into the intergalactic medium. When jets plow into the surrounding gas, they create shock waves and heat the gas to temperatures of tens of millions of degrees, preventing it from cooling and falling back into the galaxy to form new stars. There's also a more gentle mode of feedback, sometimes called radio mode or maintenance mode, where the black hole isn't violently ejecting material, but is steadily heating its environment through jets or winds. This steady heating can balance the cooling of gas in the galaxy's halo, maintaining a situation where the gas never cools enough to collapse and form stars. This mode is thought to be important in massive elliptical galaxies and galaxy clusters, explaining why these systems have so much hot gas around them but form so few new stars. The importance of this coevolution is seen in the tight correlations between black hole mass and galaxy properties. The most famous is the M-sigma relation, which connects the black hole's mass to the velocity dispersion of stars in the galaxy's bulge. Velocity dispersion is a measure of how fast stars are moving randomly in the bulge. Higher velocity dispersion means the stars are moving faster, which requires more mass to hold them in place gravitationally. The M-sigma relation says that more massive black holes are found in bulges with higher velocity dispersions, and this relation holds across more than 4 orders of magnitude in black hole mass, from 1 million to tens of billions of solar masses. Why should such a tight relation exist? The black hole, even a supermassive one, contains only about 5% of the mass of its host galaxy's bulge. It's a tiny fraction of the total mass, yet somehow the black hole knows how massive its host bulge is. The coevolution scenario explains this. As the galaxy grows through mergers and gas accretion, the black hole grows as well, fed by gas flowing into the nucleus. But when the black hole becomes luminous enough, its feedback begins to suppress further gas inflow, limiting both continued star formation in the bulge and further growth of the black hole. The equilibrium between growth and feedback naturally produces a correlation between black hole mass and bulge mass, and in turn, the galaxy's supply of gas feeds the black hole, making it grow. Gas that loses angular momentum through various processes, interactions with other gas, shocks, turbulence, can fall toward the galactic center and feed the black hole. The relationship was thought to be entirely centered in the galaxy's nucleus, the core, a tight, mutually dependent system where the black hole and galaxy are locked in a regulatory feedback loop that determines their joint evolution. But the Infinity Galaxy discovery challenges this neat picture. If supermassive black holes can form in intergalactic space, divorced from any galaxy nucleus, then the co-evolution story becomes more complicated. These black holes form without any pre-existing galaxy, without any bulge to correlate with. They're born in the chaos of colliding gas clouds, not through the slow, regulated process of co-evolution. This suggests that there might be multiple pathways to forming supermassive black holes, and the co-evolution mechanism, while important, isn't the only game in town. Moreover, if collision-induced direct collapse can produce million solar mass black holes in just a few million years, these objects could quickly become significant players in their environments. A million solar mass black hole, while smaller than the black holes in the galactic nuclei, is still massive enough to influence gas dynamics and star formation over thousands of light years. If these objects are common, they could represent a hidden population of black holes that traditional surveys might miss, especially if they're between episodes of active feeding and thus not shining brightly. The discovery also raises questions about the ultimate fate of these orphan black holes. Will the black hole in the Infinity Galaxy's void eventually fall into one of the merging galaxies and become a normal nuclear black hole? Or could it remain free-floating in intergalactic space indefinitely? The answer depends on the details of the merger and the dynamical interactions between the 3 black holes, but it's quite possible that this orphan could eventually merge with one of the nuclear black holes, contributing its mass to the final merged black hole at the center of the post-collision galaxy. And in turn, the galaxy's supply of gas feeds the black hole, making it grow. Gas that loses angular momentum through various processes, interactions with other gas, shock, turbulence, can fall toward the galactic center and feed the black hole. The relationship was thought to be entirely centered in the galaxy's nucleus, the core, a tight, mutually dependent system where the black hole and galaxy are locked in a regulatory feedback loop that determines their joint evolution. But now we have an SMBH that formed outside the nucleus, entirely from collision-stripped gas. If supermassive black holes can form so dynamically in the intergalactic medium, it completely changes how we model their growth. It suggests there is a second, powerful pathway for SMBH formation that happens not through slow, steady growth in a galactic core, but through catastrophic, violent events in the space between galaxies. This discovery suggests that the relationship between a black hole and its host galaxy is more flexible and less rigid than previously assumed, potentially creating a whole new category of wandering or outskirt SMBHs that wander through space and shape the cosmos in ways we haven't accounted for in our simulations. Computer simulations of galaxy evolution typically assume that SMBHs form and grow at the centers of galaxies. If SMBHs can also form in intergalactic space during collisions, these simulations may be missing an important piece of the puzzle. If these objects are more common than we thought, they could be playing a huge, invisible role in pushing gas around and changing the shape of galaxies far from the central nucleus. An SMBH in the intergalactic medium could affect the distribution and dynamics of gas across the entire collision zone, influencing where and how stars form, and potentially affecting the final structure of the merged galaxy that will result from the collision. This finding expands the possibilities of black hole formation from a single, centralized process to a much more dynamic, environmentally triggered one. This opens up exciting new questions for future research. How common are these collision-induced direct collapse black holes? Are they a rare curiosity, or do they represent a significant fraction of all SMBH formation events throughout cosmic history? Could similar processes occur in other extreme environments, such as in the densest parts of galaxy clusters where multiple galaxies are interacting simultaneously? What happens to these orphan black holes in the long term? Do they eventually fall into one of the merging galaxies and become a normal galactic nucleus black hole? Or can they remain free-floating for billions of years? Answering these questions will require extensive observational campaigns with current and future telescopes. Webb will continue to survey colliding galaxies across the universe, looking for additional examples of these orphan black holes. Each discovery will help constrain how common the phenomenon is and under what conditions it occurs. Are head-on collisions required, or can glancing collisions also produce direct collapse? Does it happen primarily at specific cosmic epochs, or is it possible throughout the universe's history? Ground-based observatories will also play crucial roles. Large radio telescope arrays like the VLA and ALMA can map the distribution and dynamics of gas in colliding galaxies, providing crucial information about the conditions that might trigger direct collapse. X-ray observatories like Chandra and the upcoming Athena mission will continue to identify and characterize active black holes, measuring their masses, accretion rates, and energy output. Combining observations across all wavelengths, radio, infrared, optical, X-ray, gives us the most complete picture of these complex systems. Theorists will need to develop more sophisticated computer simulations of galaxy collisions, incorporating the physics of direct collapse and tracking the formation and evolution of multiple black holes. Current simulations typically include supermassive black holes at galactic centers but don't account for the possibility of new black holes forming in intergalactic gas. Adding this physics to the simulations will help us understand not just whether direct collapse can occur in collisions, but how often it occurs and what impact it has on galaxy evolution. There are also implications for our understanding of the early universe. If direct collapse can occur in metal-rich gas given sufficiently extreme conditions, this opens up new possibilities for forming supermassive black holes in the first few 100 million years after the Big Bang. The early universe was inherently more violent and turbulent than today, with structures forming and colliding in rapid succession. Perhaps the first supermassive black holes formed not in pristine gas clouds, but in collision zones where primordial galaxies smashed together, creating extreme conditions similar to what we see in the Infinity Galaxy. This would help resolve the tension between the light seed model and observations of extremely massive black holes at high redshift. Instead of requiring billions of years of slow growth or the special conditions of pristine gas, perhaps the early universe's violence itself was the key ingredient, creating conditions for direct collapse through dynamics rather than chemistry. Future observations with Webb of the highest redshift galaxies will test this hypothesis by looking for signatures of direct collapse in the earliest cosmic epochs. Another intriguing possibility is that collision-induced direct collapse might explain some of the missing black holes that theorists predict should exist but haven't been observed. Simulations of galaxy formation predict that there should be many intermediate mass black holes in the mass range between stellar black holes and supermassive black holes, roughly 1,000 to 100,000 solar masses. But observationally, this mass range is relatively empty, leading to what's sometimes called the intermediate mass black hole problem. Perhaps some of these missing black holes are orphans formed through collision-induced direct collapse, but now wandering in intergalactic space or in the outskirts of galaxies, too faint to be easily detected unless they happen to be actively feeding. This story is only just beginning, and we can already look into the future to predict the future of the collision. We now know that the Infinity Galaxy System is host to 3 active massive black holes, all surrounded by incredibly dense gas. According to the absolute laws of gravity, this is not a stable arrangement. 3 body systems are fundamentally chaotic, unlike 2 body systems which can have stable, periodic orbits that last forever. The 3 black holes are currently orbiting each other in a complex, chaotic gravitational dance, known in physics as the gravitational 3-body problem. The 3-body problem is famous in physics for having no general analytical solution. Unlike the 2-body problem, which Isaac Newton solved completely centuries ago, the 3-body problem must generally be solved numerically, case by case, using computers. Predicting the precise motions of 3 orbiting objects is famously difficult, and small changes in initial conditions can lead to dramatically different outcomes, a hallmark of chaotic systems. But despite this unpredictability in detail, the ultimate fate is certain. The system cannot remain in its current configuration indefinitely. Over the next millions, or perhaps even billions of years, the process of dynamical friction will take hold. Dynamical friction is a sort of gravitational drag. It happens because as the 3 objects move through the dense gas and stars, they create a wake of gravitational disturbance that slows them down, causing them to lose energy. Imagine moving through a pool of water. You create a wake behind you, and creating that wake takes energy, which comes from your motion, slowing you down. Similarly, massive objects moving through a sea of stars and gas create gravitational wakes that extract energy from their motion. This drag will cause the 3 SMBHs to slowly but surely spiral inward and merge. This will be a multi-stage process playing out over cosmological timescales. First, the black hole in the void will likely fall back into the densest region of the collision. Since it's currently in intergalactic space, it will be pulled by the gravity of the merging galaxies toward regions of higher density. Depending on exactly where it ends up and how the collision evolves, it might fall into one of the 2 galactic nuclei, or it might remain in the core of the newly merged galaxy that will form. Then, 2 of the black holes will merge, creating a pair which will then violently merge with the 3rd. The exact sequence depends on the details of the orbits and interactions, but eventually, all 3 will come together. When 2 black holes finally get close enough, they enter a phase called the gravitational wave-driven inspiral, where they orbit each other rapidly while losing energy to gravitational waves, spiraling closer and closer until they merge in a fraction of a second in a final cataclysmic event. The final result will be a single, even larger supermassive black hole, a true behemoth, residing at the new center of the completely merged final galaxy. The final mass will be the sum of all 3, an object likely reaching many billions of solar masses. If we estimate the 2 galactic nucleus black holes at 500 million solar masses each, and add the 1 million solar mass black hole from the void, though in reality all 3 will have grown larger by the time they do merge, we could end up with a black hole of over 1 billion solar masses, potentially significantly more if the black holes continue feeding on gas before they merge. This final merging event will be one of the most powerful phenomena in the universe. When 2 black holes finally collide, they shake the very fabric of space-time itself, releasing an enormous final burst of energy in the form of gravitational waves, ripples in the universe that propagate at the speed of light. These gravitational waves are distortions of space-time itself, literally stretching and squeezing space as they pass. They were predicted by Einstein's general theory of relativity over a century ago, but were only directly detected for the first time in 2015 by the LIGO Observatory. The merger of supermassive black holes in the billion solar mass range produces gravitational waves at frequencies too low for current ground-based detectors like LIGO to detect. LIGO is sensitive to the higher frequency waves produced by merging stellar mass black holes. But future space-based detectors, particularly the Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s, will be specifically designed to detect gravitational waves from supermassive black hole mergers. To understand why we need different detectors for different masses of black holes, we need to understand how gravitational waves work. When 2 black holes orbit each other, they create ripples in space-time that propagate outward at the speed of light. The frequency of these gravitational waves is related to the orbital frequency of the black holes. Essentially, the waves have a frequency about twice the orbital frequency. As the black holes spiral closer together, they orbit faster, and the gravitational waves increase in frequency and amplitude, creating a characteristic chirp signal. For stellar mass black holes of 10 to 100 solar masses, this chirp sweeps through frequencies of tens to thousands of hertz in the final seconds before merger, frequencies that LIGO's 4-kilometer-long interferometer arms can detect. LIGO works by bouncing laser light back and forth along two perpendicular arms and looking for tiny differences in the light travel time caused by gravitational waves stretching and squeezing space. When a gravitational wave passes through LIGO, it stretches space in one direction while squeezing it in the perpendicular direction, causing the two laser beams to go slightly out of phase with each other. This phase difference creates an interference pattern that can be measured with extraordinary precision. The sensitivity is astounding. LIGO can detect changes in arm length smaller than 1,000th the diameter of a proton. To put this in perspective, if the distance from Earth to the nearest star, Proxima Centauri, were stretched by the width of a human hair, LIGO could detect it. This incredible sensitivity is necessary because gravitational waves are extraordinarily weak, even from the most violent cosmic events. Space-time is remarkably stiff, resisting distortion, which is why it takes objects as massive and compact as black holes, moving at relativistic speeds, to produce detectable gravitational waves. But supermassive black hole mergers are different. A pair of billion solar mass black holes orbits each other much more slowly than stellar mass black holes because their larger separation means lower orbital velocities according to Kepler's laws. The gravitational waves they produce have much lower frequencies, typically in the range of 0.001 to 0.1 Hertz, thousands of times lower than LIGO's sensitive band. At these low frequencies, you can't use a ground-based detector because seismic noise, vibrations from earthquakes, ocean waves, even traffic, completely overwhelms the signal. This is where LISA comes in. LISA will consist of 3 spacecraft flying in a triangular formation with each side of the triangle about 5 million kilometers long, roughly 6 times the Earth-Moon distance. Laser beams will bounce between the spacecraft, and the entire constellation will orbit the Sun, trailing about 50 million kilometers behind Earth. At this scale, and in the quiet of space, LISA will be sensitive to the low-frequency gravitational waves from supermassive black hole mergers. LISA will be able to detect merging supermassive black holes anywhere in the observable universe, providing a complete census of these events. When the final black holes in the infinity galaxy system merge, billions of years from now, they will produce gravitational waves that LISA or its successor instruments may be able to pick up, telling the final violent chapter of the infinity galaxy's dramatic life. If we're still observing with gravitational wave detectors in a few billion years, and hopefully humanity or its successors will be, we might actually witness this merger. The gravitational wave signal would arrive years or decades before the electromagnetic signal because the gravitational waves are emitted from deeper in the potential well, from the final moments when the black holes are just light minutes apart, while the electromagnetic emission comes from larger scales where gas is being disrupted. The amount of energy released in the final moments of the merger will be enormous, a gravitational roar echoing across the universe. In the final second of the merger, the energy released in gravitational waves can exceed the light output of all the stars in the observable universe combined, making it one of the most energetic events in the cosmos. To be more specific, a billion solar mass black hole merger might release about 5% of the total mass energy as gravitational waves, according to Einstein's ERMC2. This works out to about 50 million solar masses worth of energy, all released in less than a minute. For comparison, our Sun will release about 1 Earth mass worth of energy over its entire 10 billion year lifetime. The black hole merger releases millions of times more energy in seconds. This energy doesn't disappear. It propagates outward as gravitational waves, literally rippling the fabric of space-time across the cosmos. When these waves eventually reach Earth billions of years from now, they'll be greatly weakened by spreading over such vast distances, but they'll still be detectable by sufficiently sensitive instruments. The gravitational wave signature will tell us the masses of the merging black holes, their spins, and even potentially details about how much gas was present during the merger by looking for electromagnetic counterparts to the gravitational wave signal. When the final black holes in the infinity galaxy system merge, billions of years from now, they will produce gravitational waves that LISA, or its successor instruments, may be able to pick up, telling the final, violent chapter of the infinity galaxy's dramatic life. The amount of energy released in the final moments of the merger will be enormous, a gravitational roar echoing across the universe. In the final second of the merger, the energy released in gravitational waves can exceed the light output of all the stars in the observable universe combined, making it one of the most energetic events in the cosmos. The merger will also produce what's called a quasar, or active galactic nucleus, or AGN, as the newly merged black hole settles into its new configuration and feasts on the gas available in the merged galaxy. This AGN phase could last for millions of years, during which the merged black hole and its surroundings would shine so brightly that they could be detected across the entire observable universe. Eventually, as the gas supply is exhausted or blown away by feedback, the black hole will settle into a quiescent state, becoming a dormant giant at the heart of a massive elliptical galaxy. Finally, the most profound implication of the infinity galaxy is that it is a literal time machine, allowing us to go looking back in time. This isn't just a metaphor, it's a direct consequence of the finite speed of light and the vast distances involved in astronomy. The collision is 8 billion light years away, which means we're seeing it as it was 8 billion years ago. While that's far by any human standard, it's considered relatively nearby when compared to the black holes that formed only a few 100 million years after the Big Bang, which are now over 13 billion light years away, visible at red shifts of z-7 or higher. The infinity galaxy collision acts as a physical laboratory for the conditions that existed in the young universe. This is a profound and powerful idea. We can study events happening recently, at least on cosmic timescales, that replicate conditions from the early universe. The violent crash has created environments that are functionally identical to the environments of the early cosmos, environments that were thought to be necessary for the direct collapse model to work. Specifically, the immense shock-induced compression of gas in the central region of the crash mimics the naturally high-density, high-pressure environments of the young cosmos, environments that were thought to be necessary for the direct collapse model to work. In the early universe, shortly after the Big Bang, matter was distributed more uniformly and densely than today. As the first structures began to form, gas would collapse into dense clumps under gravity, and in some special circumstances, these clumps could reach the extreme densities and pressures needed for direct collapse. The discovery essentially proves that if you can create high enough density and high enough pressure, a massive cloud of gas will collapse into a supermassive black hole, even if that gas is old and metal-rich. This removes the necessity of pristine gas and replaces it with the necessity of extreme pressure as the key ingredient. The paradigm shift here is significant. Pristine gas was thought to be essential because it can't cool efficiently, preventing fragmentation. But what the infinity galaxy shows is that if you raise the pressure and temperature high enough through other means, in this case, collision shockwaves, you can achieve the same result: suppression of fragmentation and direct collapse to a black hole. This means the process for making the first giant black holes in the early universe was likely a dynamic and violent process, and we are seeing its modern-day rerun right now in the infinity galaxy. The early universe was a violent place, filled with collisions and mergers as the first structures formed. If these violent events could trigger direct collapse, it provides a natural explanation for how supermassive black holes could form so quickly in the early cosmos. We may be witnessing in the infinity galaxy a process that was common in the first billion years after the Big Bang, but is rarer today because the modern universe is less dense and violent on average. By studying this relatively nearby event, we gain invaluable insight into the processes that kick-started the formation of the largest structures in the entire universe. Instead of just theorizing about what might have happened in the early universe based on simulations and indirect evidence, we can now study an actual direct collapse event, or at least what appears to be one, in detail. We can measure the exact conditions required, the properties of the gas, the role of shock waves, the timescales involved, and use all this information to refine our models of black hole formation in the early universe. The universe is far more capable of producing its own monsters than we ever suspected. Time and again, astronomical observations have revealed that the universe is more creative, more violent, and more capable of extremes than our theories anticipated. The Infinity Galaxy is the latest example of this pattern, showing us that nature has found a way to create supermassive black holes through mechanisms we hadn't fully appreciated, in places we didn't expect them to be. The philosophical implications of this discovery extend beyond just black hole physics. It reminds us of the fundamental nature of scientific progress. Our knowledge is always incomplete, our theories always provisional. What we call scientific laws are really just our best current descriptions of how nature behaves, based on the observations we've been able to make so far. When new observations contradict our expectations, we don't discard the scientific method. We revise our understanding to accommodate the new data. This iterative process is what makes science so powerful. Each generation of telescopes and instruments reveals phenomena that previous generations couldn't have imagined. Galileo's first telescope revealed moons orbiting Jupiter, challenging the idea that everything orbited Earth. Hubble's observations of galaxies revealed the expansion of the universe, overturning the static universe model that Einstein himself initially preferred. Now Webb is revealing supermassive black holes forming in impossible places, forcing us once again to expand our understanding. The Infinity Galaxy also highlights the importance of multi-wavelength astronomy. No single telescope or instrument could have made this discovery alone. It required observations from radio telescopes, X-ray observatories, and infrared space telescopes, each contributing a piece of the puzzle. The radio observations revealed the black hole's emissions and helped measure its velocity. The X-ray data showed the high-energy processes occurring near the black hole, and Webb's infrared observations penetrated the dust to reveal the surrounding gas and measure its properties. Only by combining all these observations could astronomers piece together the full story. This collaborative, multi-wavelength approach is increasingly the norm in modern astronomy. Individual telescopes and observatories don't compete so much as complement each other, each contributing unique capabilities to a collective effort to understand the cosmos. This cooperative model of science, where researchers from around the world work together and share data openly, has accelerated the pace of discovery dramatically. This incredible journey through the Infinity Galaxy has brought us to a stunning conclusion. The observation by the James Webb Space Telescope provides the strongest, most direct observational evidence yet for a direct collapse mechanism that creates supermassive black holes. While definitively proving the direct collapse label, a process that happens completely hidden inside a gas cloud, remains a difficult task, the evidence here is overwhelmingly strong. Before we wrap up, it's worth considering what this discovery means for our broader understanding of extreme environments in the universe. The collision zone between two galaxies represents one of the most extreme environments we can observe, with densities, temperatures, pressures, and turbulence all pushed to their limits. The fact that such environments can create supermassive black holes suggests that wherever sufficiently extreme conditions exist, nature finds ways to create remarkable structures. This principle might apply beyond galaxy collisions. Dense star clusters in the cores of galaxies experience extreme densities and frequent stellar collisions. Could these environments also trigger direct collapse? What about the cores of the densest galaxy clusters, where multiple large galaxies orbit in a relatively small volume? Could the cumulative effect of many weak interactions create conditions extreme enough for direct collapse? These questions define new frontiers for research. There's also the question of what other exotic objects might form in these extreme environments. We've focused on black holes, but galaxy collisions also create other interesting phenomena. For instance, they can trigger the formation of globular clusters, dense balls of millions of stars that orbit galaxies. They can create tidal dwarf galaxies, small galaxies formed from material stripped out of the colliding galaxies. Could there be other classes of objects as yet undiscovered that form only in these most extreme conditions. The study of the infinity galaxy also demonstrates the power of using extreme environments as natural laboratories. Physics on Earth is limited to temperatures, pressures, and densities that we can create in our laboratories, which, while impressive, pale in comparison to what the universe routinely produces. Galaxy collisions, neutron stars, black hole mergers, supernovae, these cosmic phenomena test physics under conditions we could never replicate terrestrially. By observing and studying these natural experiments, we extend our understanding of physics far beyond what laboratory experiments alone could teach us. We cannot directly see inside the gas cloud as it collapses. Even JWST's infrared vision has limits. The actual collapse process, if it happened, would have occurred over perhaps only a few million years, a cosmic eye blink, and we're seeing the system perhaps tens of millions of years after that collapse completed. We're seeing the result, a million solar mass black hole in intergalactic space. But we didn't watch it form. However, the circumstantial evidence is compelling and points strongly to direct collapse as the formation mechanism. It's worth pausing to appreciate the extraordinary technological achievement that made this discovery possible. The James Webb Space Telescope represents the culmination of decades of engineering innovation, involving contributions from thousands of scientists, engineers, and technicians across multiple countries. The telescope's 5-meter primary mirror, composed of 18 hexagonal segments made of beryllium and coated with gold, had to be designed to unfold in space like an impossibly complex origami sculpture. Each mirror segment can be individually adjusted with nanometer precision to maintain perfect alignment. The entire observatory had to be designed to withstand the violent shaking of launch on a rocket, then unfold and deploy itself perfectly in the coldness of space with no possibility of hands-on repairs. The sunshield deployment alone involved hundreds of release mechanisms that all had to work perfectly in sequence. The fact that the deployment succeeded flawlessly is a testament to the incredible dedication and skill of the engineering teams. And it's not just Webb. The discovery required data from Chandra, an X-ray observatory launched in 1999 that continues to provide crucial high-energy observations. It required data from the VLA, a ground-based radio telescope array in New Mexico that has been observing the universe since 1980. These older facilities, maintained and upgraded over decades, remain essential parts of our astronomical toolkit. The discovery also benefited from archival Hubble observations that provided context and comparison. Modern astronomical discoveries are thus built on decades of infrastructure and observation, with new facilities like Webb adding capabilities rather than replacing older instruments. Looking forward, what might future observations reveal about the infinity galaxy and systems like it? Webb itself will continue, observing the system, potentially catching changes in the black hole's brightness as their accretion rates vary.